Grounding a 480 volts power supply directly to an aluminum walkway is not sufficient for ensuring electrical safety. The National Electrical Code, also known as NEC, and the Occupational Safety and Health Administration, known as OSHA, have specific requirements for grounding electrical equipment to protect personnel and prevent hazards. Metal walkways and equipment enclosures need to be effectively grounded to prevent the accumulation of electrical charge and to minimize the risk of electric shock. Aluminum, while conductive, presents unique challenges due to its tendency to form an oxide layer on its surface. This oxide layer acts as a high-resistance barrier, impeding the flow of fault current between the walkway and the electrical equipment. This high-resistance connection compromises the effectiveness of the grounding system and elevates the risk of electrical shock in the event of a fault. To establish a proper and reliable grounding system, several steps should be taken. Firstly, install a copper ground rod near the aluminum walkway. A copper ground rod provides a low impedance path to earth, ensuring that fault currents can be safely dissipated. The ground rod should be at least 8 feet long and driven deep into the earth to achieve effective grounding. Secondly, bond the aluminum walkway to the copper ground rod using a suitable bonding conductor. This connection creates a direct electrical pathway between the walkway and the ground rod, bypassing the high-resistance aluminum oxide layer. A copper wire or ground braid can be used as the bonding conductor. The size of the conductor should be selected based on the size of the overcurrent protection device protecting the circuit, in accordance with NEC Table 250.122. Thirdly, ensure a low-resistance connection between the bonding conductor, the aluminum walkway, and the copper ground rod. Clean the surfaces of the aluminum walkway and the copper ground rod to remove any dirt, corrosion, or coatings that could impede electrical conductivity. Use a grounding clamp or other appropriate method to securely connect the bonding conductor to both the walkway and the ground rod. The connection points should be mechanically sound and resistant to corrosion. Additional considerations for maintaining a reliable grounding system include the following. The grounding system should be inspected and tested regularly to verify its integrity. This involves visually inspecting the connections for corrosion or damage and using a ground resistance tester to measure the resistance of the grounding system. A low resistance reading indicates a good ground connection. If the walkway is painted or coated, the paint or coating may need to be removed at the connection points to ensure a good electrical connection. Paint and coatings can act as insulators, preventing proper electrical contact. Consult with a qualified electrician to ensure that the grounding system meets all applicable codes and safety standards. A qualified electrician can assess the specific requirements of the installation and ensure that the grounding system is properly designed and installed. Grounding is essential for electrical safety, and it is important to adhere to all applicable codes and standards. The NEC provides detailed requirements for grounding electrical systems and equipment. These requirements are designed to protect people and property from electrical hazards. Some relevant NEC sections related to grounding include Article 250, which covers grounding and bonding, Section 250.4, which discusses general requirements for grounding, Section 250.24, which covers grounding service supplied alternating current systems, and Section 250.50, which covers grounding electrode systems. OSHA also has regulations related to electrical safety. These regulations require employers to provide a safe workplace for their employees. This includes ensuring that electrical equipment is properly grounded and that employees are trained on electrical safety procedures. Some relevant OSHA regulations related to grounding include 29 Code of Federal Regulations 1910.304, which covers wiring design and protection, and 29 Code of Federal Regulations 1910.305, which covers wiring methods, components, and equipment for general use. The purpose of grounding is to provide a low impedance path for fault current to flow back to the source. This allows the overcurrent protection device, such as a circuit breaker or fuse, to quickly trip and de-energize the circuit, preventing electrical shock or fire. A properly grounded system also helps to reduce voltage fluctuations and improve the stability of the electrical system. When a fault occurs in an ungrounded system, the voltage can rise to dangerous levels, increasing the risk of electric shock. Grounding provides a reference point for the voltage, preventing it from rising to unsafe levels. The size of the grounding conductor is important. The grounding conductor must be large enough to safely carry the maximum fault current that could flow in the event of a fault. The NEC provides tables that specify the minimum size of the grounding conductor based on the size of the overcurrent protection device protecting the circuit. It's critical to use the correct size grounding conductor to ensure that it can safely carry the fault current. The type of grounding electrode is also important. A ground rod is a common type of grounding electrode, but other types of grounding electrodes are also permitted by the NEC. These include metal underground water pipes, metal building frames, and concrete encased electrodes. The type of grounding electrode used should be selected based on the specific site conditions and the requirements of the NEC. The location of the grounding electrode is also important. The grounding electrode should be located as close as possible to the electrical equipment being grounded. This minimizes the length of the grounding conductor and reduces the impedance of the grounding path. The grounding electrode should also be located in an area where it will be in contact with the earth year-round. In areas with dry soil conditions, it may be necessary to use multiple ground rods or other methods to improve the effectiveness of the grounding system. The connection between the grounding conductor and the grounding electrode must be made using a listed connector. Listed connectors are designed to provide a reliable electrical connection that will not corrode or loosen over time. The connection should be made in accordance with the manufacturer's instructions. It is important to never rely on the aluminum walkway itself as the sole grounding conductor. While aluminum is a conductive material, its conductivity is lower than that of copper. Additionally, the aluminum oxide layer that forms on the surface of aluminum can significantly increase the resistance of the connection. This higher resistance can prevent the proper flow of fault current and increase the risk of electric shock. In addition to grounding the electrical equipment, it is also important to bond the metal parts of the equipment together. Bonding is the process of connecting all metal parts of the equipment together to create a common ground potential. This helps to prevent voltage differences between different parts of the equipment, which can create a shock hazard. Bonding is typically accomplished by using bonding jumpers, which are short lengths of wire that connect the metal parts of the equipment together. The size of the bonding jumper should be selected based on the size of the overcurrent protection device protecting the circuit. The NEC provides tables that specify the minimum size of the bonding jumpers. It is also important to bond the metal parts of the building together. This includes bonding the metal water pipes, metal gas pipes, and metal building frame together. Bonding the metal parts of the building together creates a common ground potential throughout the building, which helps to prevent voltage differences and reduce the risk of electric shock. The bonding of the metal parts of the building should be done in accordance with the requirements of the NEC. Regular inspection and testing of the grounding system is essential to ensure that it is functioning properly. The grounding system should be visually inspected for any signs of damage or corrosion. The connections should be checked to ensure that they are tight and secure. The resistance of the grounding system should be measured using a ground resistance tester. A high resistance reading indicates a problem with the grounding system. The grounding system should be tested at least annually and more frequently in areas with corrosive environments. If any problems are found with the grounding system, they should be corrected immediately. It is important to remember that grounding is not a substitute for other safety measures, such as using ground fault circuit interrupters, known as GFCIs, and wearing personal protective equipment, known as PPE. GFCIs are designed to protect people from electric shock by quickly tripping the circuit when a ground fault is detected. PPE, such as rubber gloves and insulated tools, can protect workers from electric shock. Grounding, GFCIs, and PPE are all important parts of a comprehensive electrical safety program. In summary, grounding a 480 volts power supply to an aluminum walkway is not sufficient for ensuring electrical safety. It is essential to install a copper ground rod, bond the walkway to the ground rod, and ensure a low resistance connection. Regular inspection and testing of the grounding system is also important. By following these steps, you can ensure that the electrical system is properly grounded and that people and property are protected from electrical hazards. Always consult with a qualified electrician to ensure that the grounding system meets all applicable codes and safety standards. Understanding grounding principles is paramount for anyone working with or around electrical systems. It is the cornerstone of electrical safety, protecting individuals from potential hazards such as electric shock and fire. The integrity of the grounding system hinges on creating a low-impedance path for fault currents to safely return to the source, thereby facilitating the swift operation of overcurrent protection devices like circuit breakers or fuses. Aluminum walkways, while seemingly conductive, present unique challenges due to the formation of an aluminum oxide layer. This layer, acting as a formidable barrier, significantly impedes the flow of fault currents, rendering direct grounding to the walkway inadequate. To mitigate this risk, a meticulously engineered grounding system is imperative. The cornerstone of this system is the installation of a dedicated copper ground rod, strategically positioned proximate to the aluminum walkway. This ground rod serves as the primary conduit for fault currents, channeling them directly to the earth. Its dimensions, adhering to NEC standards, typically mandate a minimum length of 8 feet, ensuring deep penetration into the earth for optimal conductivity. The next crucial step involves establishing a robust bond between the aluminum walkway and the copper ground rod. This connection, facilitated by a suitable bonding conductor such as a copper wire or ground braid, creates a seamless electrical pathway bypassing the insulating aluminum oxide layer. The selection of the bonding conductor size is governed by NEC Table 250.122, which correlates conductor size to the rating of the overcurrent protection device safeguarding this circuit. Ensuring a low resistance connection is paramount to the efficacy of the grounding system. Thoroughly cleaning the surfaces of both the aluminum walkway and the copper ground rod is essential to remove any contaminants that could impede electrical conductivity. Utilizing listed grounding clamps or other appropriate connectors ensures secure and corrosion-resistant connections, maintaining the integrity of the grounding path over time. Beyond the initial installation, regular inspection and testing are indispensable for verifying the ongoing effectiveness of the grounding system. Visual inspection should be conducted to identify any signs of corrosion, damage, or loose connections. Ground resistance testing, performed using specialized equipment, quantifies the resistance of the grounding system, providing valuable insights into its performance. Low resistance readings signify a healthy grounding system, while elevated readings necessitate immediate attention and corrective action. The NEC, a comprehensive compilation of electrical safety standards, provides detailed guidelines for grounding and bonding electrical systems. Article 250 within the NEC is dedicated to grounding and bonding requirements, encompassing essential aspects such as general grounding principles, grounding of alternating current systems, and the establishment of effective grounding electrode systems. Compliance with the NEC is not merely a matter of adherence, but a fundamental obligation to ensure the safety of personnel and property. OSHA, vested with the authority to enforce workplace safety regulations, mandates that employers provide a safe working environment for their employees. This entails ensuring that electrical equipment is properly grounded and that employees receive comprehensive training on electrical safety protocols. OSHA regulations, outlined in 29 Code of Federal Regulations 1910.304 and 1910.305, address wiring design, protection, and acceptable wiring methods, components, and equipment for general use. Grounding serves a multifaceted purpose, not limited to personnel protection. It also plays a vital role in mitigating voltage fluctuations and stabilizing the electrical system. Ungrounded systems are prone to voltage spikes during fault conditions, posing a significant risk of electric shock. Grounding mitigates this risk by providing a stable reference point for voltage, preventing it from escalating to dangerous levels. The selection of appropriate grounding electrodes is crucial for achieving effective grounding. While ground rods are commonly employed, alternative grounding electrodes such as metal underground water pipes, metal building frames, and concrete encased electrodes are permissible under the NEC. The choice of grounding electrode should be tailored to the specific site conditions and comply with NEC requirements. The placement of the grounding electrode is equally critical. Ideally, it should be situated as close as feasible to the electrical equipment being grounded, minimizing the length of the grounding conductor and reducing impedance. Furthermore, the grounding electrode should be located in an area that ensures consistent contact with the earth throughout the year. In arid regions characterized by dry soil conditions, employing multiple ground rods or other augmentation techniques may be necessary to enhance the effectiveness of the grounding system. The connection between the grounding conductor and the grounding electrode must be meticulously executed using listed connectors. These connectors are specifically designed to establish reliable, corrosion-resistant electrical connections, ensuring long-term grounding integrity. Adhering strictly to the manufacturer's instructions during installation is paramount. The aluminum walkway should never be considered as the sole grounding conductor. While aluminum exhibits conductive properties, its conductivity pales in comparison to that of copper. Moreover, the inherent aluminum oxide layer adds significant resistance, compromising the grounding path's efficacy. In addition to grounding the electrical equipment, bonding all metal components of the equipment together is imperative. Bonding entails connecting all metal parts to create a common ground potential, thereby preventing voltage differentials and minimizing shock hazards. Bonding jumpers, typically short lengths of wire, are employed to interconnect metal components, ensuring electrical continuity. Bonding extends beyond individual equipment to encompass the building's metal infrastructure, including water pipes, gas pipes, and the building frame itself. Interconnecting these metal components establishes a comprehensive ground potential throughout the building, mitigating voltage discrepancies and reducing the risk of electrical shock. Adherence to NEC guidelines is crucial for ensuring proper bonding practices. Regular inspection and testing of the grounding system are non-negotiable. These proactive measures ensure that the grounding system functions flawlessly, providing continuous protection against electrical hazards. Visual inspections should be conducted to identify any signs of damage, corrosion, or loose connections. Ground resistance testing, performed at least annually and more frequently in corrosive environments, quantifies the resistance of the grounding system, providing invaluable insights into its performance. Any deficiencies identified during inspection or testing must be rectified promptly to maintain the integrity of the grounding system. Grounding, while indispensable, should not be regarded as a substitute for other essential safety measures. GFCIs provide an additional layer of protection by swiftly interrupting the circuit when a ground fault is detected, preventing an electric shock. PPE, such as insulated gloves and tools, safeguards workers from electrical hazards, further enhancing their safety. Grounding, GFCIs, and PPE constitute a comprehensive electrical safety program, working synergistically to minimize risks and protect personnel. In conclusion, grounding a 480 volts power supply to an aluminum walkway is inherently insufficient for ensuring electrical safety. A properly engineered grounding system, incorporating a dedicated copper ground rod, a robust bond between the walkway and the ground rod, and meticulous attention to connection integrity is essential. Regular inspection and testing, coupled with compliance with NEC and OSHA regulations, guarantee the long-term effectiveness of the grounding system, safeguarding people and property from the perils of electricity. Consulting with a qualified electrician is paramount to ensure that the grounding system meets all applicable codes and safety standards, providing peace of mind and ensuring a safe electrical environment. Remember that electricity can be very dangerous and proper precautions should always be taken. If you are not qualified, always have a licensed electrician do the work for you.